Okay, let's continue with aggregation and segregation. Okay, and the first type of models I want to introduce in this video is called scaling models. Um, this type of model was proposed by Thomas Schelling. Okay, the name is after this scientist name. It was proposed in 1971. Okay, it proves that micro motives can lead to non-obvious micro behaviors. Okay, so there are different types of scaling models, but the basic rules are this. Okay, individuals of different types are randomly distributed and tolerate individuals of opposite type in their neighborhood. So here there is a concept of tolerance. Okay, at each step, individuals examine their immediate neighborhood. Of course, this neighborhood is defined by a user, and after that they can either stay put or move elsewhere depending on whether the local composition suits their preferences. Local composition means the spatial composition of neighbors, right? We have different types of individuals. If an individual is surrounded by other individuals that belong to the same type, then we say that the environment is preferred by the central cell. In summary, let's just say these individuals, they want to stay with the same type of individuals. Okay, if that is not the case, they want to move to another location to find more individuals belong to the same type. Okay, so we use a parameter called p-like to address the local composition. Okay, so a p-like is somewhere between 0 and 1. If p-like is equal to 0.7, it means that 70% of the neighbors, they belong to the same type as the central cell. Okay, repeats until everyone finds a satisfactory home or no one can move. So here it's pretty obvious that this type of models, they're going to produce segregation and aggregation, because you can say from the rules that everybody here is trying to find out a location where it can be surrounded by individuals belong to the same type, belong to its own type. Okay, so it's pretty good to simulate aggregation and segregation of human beings or animals, because no matter which species, they tend to stay with their own people, right? And the tricky part is p-like. Okay, we can always set a desired p-like from 0 to 1.0, right? From 0 to 1.0. So here we have two types of scaling models. Figure A shows one type, figure B shows another type. The difference is their the definition for satisfaction. Okay, for A, when individuals move only if the destination meets their requirement for like neighborhoods, and B, when individuals move to the best available location, even if it does not meet their requirement. Which means that for figure A, the rule is more strict. Each individual only moves when the destination meets their requirement, meets the desired p-like. On the other hand, in figure B, this model is not that strict compared to figure A. Each individual will move to a new location as long as it's the best available, which means that the P-like of the destination doesn't need to be equal to or even larger than the desired P-like. So you can see the results here. The vertical axis on the left side, on the right side, they're both for resulting P-like, which means in the end, when nobody can move, what's the distribution of P-like that's resulting P-like, right? So on the left side, we can see that as the desired P-like increases, the resulting P-like also increases. So here we have another reference here is a dashed straight line. It's where desired P-like equals resulting P-like. If your resulting P-like is well above this line, it means that everybody's situation is getting better, right, during this process. And here we have a lot of, not a lot of, several bar plots, right? And you can say when the desired P-like is smaller than 0.7, eventually, all people, all individuals, they are okay. They are satisfied with their environment, as long as your desired P-like is not too high. But if your desired P-like is too high, 0.7 or even above, and you are following the rule that if the destination, each individual only moves when the destination meets their requirement, and the requirement is too high, is above 0.7, then your resulting P-like will be relatively low, and even below this P-like, even below this desired P-like equals resulting P-like dash line. It means that if your rules are too strict and you only move when the destination is your preferred destination, and as a result, not everybody can get what they want. Okay, it means that you should not be too strict. There should be compromise. As long as the new destination is better than your current P-like, or it's the best available, you should move. And that's what you say here, right? One, as long as the location, the destination is the best available, even the P-like there is not above your desired P-like, you should move. If that's the rule, you have this result. Even your desired P-like is pretty high, eventually everybody is happy, everybody is satisfied. So this is very practical in our real world. It means that I know what you want, but sometimes maybe you should compromise to get best available. So if everybody does that, eventually, most people, I mean, this model is a very extreme abstraction of the real world. In real world, most people will be satisfied. If you are just you stick to what you want, and if that is not the case, you do not compromise on the left side, this is the result. A lot of people, they are not going to be satisfied because there is no compromise. But let's get back to the spatial context of this. So this model is pretty good for simulating segregation and aggregation, and simulate the influence from individuals' desire. Okay. Do not grab too much, and do not say that I don't accept compromise. Okay, we can see the difference. For A, up to P-like smaller than 0.7, the city will be more segregated than people prefer at the individual level. Okay, why is the city segregated? Because everybody is satisfied when the desired P-like is smaller than 0.7. If everybody is satisfied, it means that they are living with their own people, which means that the city is segregated. Okay, segregation behavior fails for p like larger than 0.7. A large number will be unhappy, which means that the resulting p like is lower than desired p like. Okay, because they only want to move when the destination has a p like equal to or larger than the desired p like. So actually, if you're using this strict rule to move, and also the desired p like is too high, then the segregation is fail. Because according to the concept of this model, each individual wants segregation, wants to live with their own with its own people. Okay, so this is a scaling model. And we have two examples in the model library of the textbook. Okay, you can play with them. And next, let's talk about spatial partitioning. Actually, we have seen spatial partitioning since the beginning of this chapter. I just didn't mention this concept. I didn't mention it. But you should know that local averaging, majority CA, other types of CA, IPS scaling models, they are all building block models for spatial partitioning, which means that they separate the whole space into small clusters, which means that there are segregation and aggregation, and they are all bottom-up models, which means that the driving force for all these models is there at individual level. Okay, for all these models, the rules, the sets of rules, they are all for individuals. Okay, each individual will follow those rules to behave, and then eventually these behaviors at individual level, they lead to a global pattern, which is segregation and aggregation. So bottom is the individual, up is the global pattern. So all these models we have discussed here, they are bottom-up models. And we also have top-down models. Okay, single overall entity driving the process instead of individuals. Here we have two examples, 3.12 subdivision and the 3.13 iterated Voronoi. Let me show you 3.12, okay? Where is that? 3.12. Subdivision. This is a very simple model. The idea here is at random select and split regions in east-west direction or north-south direction divisions. Okay. So let's get back. So set up. So we have a huge polygon here, square. We only have one square here. So this black cell is the centroid of this square. And if we go by first step, okay, you can see that huge square is divided into two squares. And now for the green square, it has the half size of the original square. So the original square was equally divided into two. The direction now is from west to east. Of course, this is random. It could be from north to south, but for that step we just experienced, it's along the direction of west to east. And now we have two squares. Next step, okay, the model will choose one of those two squares and divide it again into two smaller squares. Now we have two black centroids here, okay, because the original bottom, it's not square anymore, it's a rectangle. was divided into two squares again. Okay, if we do this, now we have three polygons. One is rectangle, two, the rest two, they are squares. The program will choose one of the three polygons and divide it into two again. Okay, equally divided. So let's say, okay, this one was divided into two. And if we let it go, this process will be repeated many times. For now, 1,333 steps, or you can say times or ticks. And now you can say that we have this spatial pattern. There are aggregations. For example, this green cluster, this green cluster, another green cluster here, and also segregation, right? All those green clusters, they are separated from each other, and each one is an aggregation. And here you can say that this process, this pattern was not created by individual, by each cell. At the very beginning, this polygon covers the whole space. It is happening from the very top level of the space, right? It is divided into smaller polygons, and even smaller, and more polygons they are created. So this process is not happening from individuals. It is happening from the whole space. This is a whole space. One polygon is a square, and it will be divided. Okay. Okay, so this is another type of spatial partitioning, because what we have discussed here, all these models, they are building block models from bottom to up. So here, you should know that this spatial partitioning could also happen from top level to individual level. Okay, and in sections 3.7, I'm going to introduce even more complicated models. Okay, let's say them. The first type I want to introduce here is called reaction-diffusion processes, or the spatial pattern they produce. How do intricate patterns emerge in the absence of complicated instructions? Which means that some very complex patterns, they could be created from very simple sets of rules. Okay, and Alan Turing, he is considered as the father of computers, right? Of computers. He asked this question in 1952: how does the rich variety of patterns of animals' codes happen? Right? For different patterns on animals' coats. Of course, some of them they are camouflage. Some of them they are they're for warnings, to warn their enemies. But how did this pattern? How did these patterns happen? Okay, so Alan Turing, he argued that patterns are caused by the interaction of a pair of chemicals called morphogens. Okay, a pair of chemicals. One triggers cell activity, the other hinders or tries to stop it. So the interaction between this simple pair of chemicals dictate where cells grow, causing intricate patterns. So it's a very simple theory. There is only a pair of chemicals. One is trying to grow, another one is trying to hinder this growth. And this very simple interaction, this very simple set of rules, they could create very complex spatial patterns on animals' coats. Okay, so you can see here, this model has its biological meaning. and it's helpful for biologists to study the pattern on animal coats and how it happened. And here is the model. Here is the model trying to simulate spots and the strips on animal coats. Okay, so a grid of cells may be in either of two states, activated or not. Simple enough, right? 0 or 1, two states. Each cell has an activation region. Okay, that's a chemical trigger cell activity. What's the other one hinders it? And an inhibition region. And this model gives two different shapes to them. Activation region is an ellipse. Okay, inhibition region is annular. Okay, cells update their state by determining the number of active cells in the activation region. That number is Na. And in their inhibition region, that number is Ni. And a rule is created to decide a cell is going to be active, to remain active or not. If this formula is true, the difference between Na and the multiplication of W and Ni is larger than 0, then cells become or remain active. And W here is the inhibition parameter. You have to assign a specific W. But here, this formula here is addressing the interaction between activation region and inhibition region. Okay, and let me show you this specific model 314. Okay, set up at the very beginning we have black cells and white cells. Okay, and of course you can set the shape for activation zone. Okay, and or activation region and also inhibition region. Okay, and set up and go. Eventually, you can say that the tick is still going, but we have a state, we have a stable state here for the whole space. Let me stop this. So we have points. We have points with different shapes. Some of them, they're actually strips, right? And some of them, they're just points. If you are looking at this whole space, it's just like the coat, animal coat on this big cat, right? So this is reaction diffusion process. It also creates segregation and aggregation, right? You can consider each white area here, each strip or point as an aggregation, and they are separated by black areas. Okay, so yeah, that's a more complex model. It's called reaction and diffusion. So there is reaction of diffusion. One triggers cell activity. When cells they are trying to spread out. They're trying to spread out. It's diffusion, and there is a reaction to this diffusion, and it is carried out by the other by the other chemical who hinders the spreading out of cells. Okay, if you consider cells with colors, they're trying to spread out. Cells with yellow and black, they're trying to spread out. Then there is a reaction to this spreading out, hinders it. You can consider that all the cells with what's this color? Yellow, right? Let's just say yellow. They are trying to stop the spreading out of black cells and dark yellow cells. That's together, this interaction spreading out and hindering this spreading out, together they form this complex, I can say, spatial pattern, right, on the coat of this big cat. Okay, and similarly for this small cat and for this beautiful fish. Okay, I will just stop here, and next in next video we're going to talk about spatial evolutionary game theory. Okay, thank you.